I want to ask you to think about something that seems completely obvious and then to notice that it is not. I want you to think about the moment when something comes into existence. The moment when there was nothing and then there was something. The moment of beginning. You have an intuitive picture of this. A new star forms when a molecular cloud collapses under gravity. There is a moment before the star exists when the cloud is just gas and dust, and a moment after when nuclear fusion has ignited in the core and the star is shining. A new life begins when an egg is fertilized, when the specific combination of genetic material comes together that will develop into a specific organism. A new thought begins when a specific pattern of neural activity emerges in a brain, a pattern that was not there before. Each of these seems to involve a moment of beginning, a transition from absence to presence, a coming into existence. Now let me tell you what the physics says about this intuitive picture. The physics says it does not correspond to anything in the laws of nature. In every physical framework we have, from the Schrödinger equation of quantum mechanics to the Einstein field equations of general relativity to the quantum field theories that describe particles and forces, there is no operation corresponding to coming into existence. The equations describe how states evolve, how configurations change, how energy is redistributed. They do not describe the creation of something from nothing. The concept of a moment when something goes from not existing to existing does not appear as a primitive operation in any physical law. This is not a minor technical point. It has radical implications for how we should think about the origin of the universe, about the nature of time, about what it means for anything to be real, and about the relationship between existence and the laws of physics. And I think most discussions of these questions, even careful philosophical and scientific ones, do not engage with this specific point at the level of precision it deserves. I want to take you through the 4 frameworks of physics that are most relevant to this question and show you, in each case, precisely why the concept of beginning to exist is missing from the physics. Then I want to put those frameworks together and ask what the absence of this concept implies for the deepest questions in cosmology and in the philosophy of existence. Let me start with the most familiar framework, classical mechanics, because even though it is not the most fundamental physical theory, it is the one in which the absence of creation is most immediately clear. Classical mechanics describes the world through configurations and their evolution. A configuration specifies the position and momentum of every particle in a system. The evolution of the configuration is governed by Newton's laws, or equivalently by Hamilton's equations, or the principle of least action. Given the configuration at any one time, the configuration at any other time, past or future, is completely determined. In this picture, nothing comes into existence. The particles that exist at one time are the same particles that existed at all earlier times and will exist at all later times. The configurations change. The arrangements of particles change. The structures they form, stars, planets, organisms, thoughts, emerge and dissolve. But the particles themselves do not appear or disappear. They simply rearrange. You might object that particles can be created and destroyed, that radioactive decay produces particles that did not previously exist, that matter and antimatter can annihilate into photons. But these processes are not the creation of something from nothing. They are the transformation of one form of energy into another. In quantum field theory, the conservation of energy ensures that the total energy of a system is preserved. When a particle is produced in a particle collision, the energy that produces it was already present in the system. The particle is a new form taken by pre-existing energy, not something created from nothing. This is the first sense in which physics does not describe the moment something begins to exist. In the law of conservation of energy, nothing is ever created from nothing. Energy is transformed from one form to another, but the total amount remains constant. The appearance of new particles is always purchased at the cost of pre-existing energy. There is no free creation. Now let me take you to quantum mechanics, where the situation is both similar and more subtle. In quantum mechanics, the state of a system is described by a quantum state, which can be thought of as a vector in a mathematical space called a Hilbert space. The evolution of the quantum state is governed by the Schrödinger equation. The Schrödinger equation is deterministic and continuous. Given the quantum state at one time, it completely determines the quantum state at any other time. The evolution is smooth, without discontinuities, without jumps, without moments where something comes into existence or ceases to exist. The quantum state of the universe, if we take seriously the idea that quantum mechanics applies to everything, including the universe as a whole, is a single continuous mathematical object that evolves smoothly through time according to the Schrödinger equation. At no point in this evolution does something new come into existence in the sense of appearing where there was previously nothing. The state changes, the probability amplitudes for different configurations change, the decoherent structure that gives rise to classical-looking world branches changes, but the state itself is always present, always evolving, always connected to its past and its future by the continuous action of the Schrödinger equation. The measurement problem in quantum mechanics complicates this picture. In the Copenhagen interpretation, when a quantum measurement is performed and an outcome is observed, the quantum state appears to collapse from a superposition to a definite state. The collapsed state is not continuously connected to the pre-measurement state by the Schrödinger equation. It involves a discontinuity, a jump. Does this represent the coming into existence of something new? I think the answer is no, for two reasons. First, in the many worlds interpretation, which I have described in detail in earlier videos, and which I believe is the most consistent interpretation of quantum mechanics, there is no collapse. The apparent jump is an artifact of looking at only one branch of a continuously evolving universal wave function. The universal wave function itself evolves smoothly and continuously without any moment of creation or destruction. Second, even in the Copenhagen interpretation, the collapsed state does not represent the creation of something from nothing. It represents the selection of a specific outcome from a pre-existing superposition. The superposition was already there. The outcome was already a component of the superposition, with a definite amplitude. The collapse did not create the outcome. It actualized it or revealed it, depending on your interpretation. Now let me take you to quantum mechanics, where the situation is both similar and more subtle. In quantum mechanics, the state of a system is described by a quantum state, which can be thought of as a vector in a mathematical space called a Hilbert space. The evolution of the quantum state is governed by the Schrödinger equation. The Schrödinger equation is deterministic and continuous. Given the quantum state at one time, it completely determines the quantum state at any other time. The evolution is smooth, without discontinuities, without jumps, without moments where something comes into existence or ceases to exist. Let me be precise about what this means. The Schrödinger equation is a first-order linear partial differential equation in time. First order means it requires only the state at one moment to determine the state at all other moments. Linear means the superposition principle holds. If state A and state B are both valid evolutions, then any linear combination of A and B is also a valid evolution. These properties together imply that the evolution is a continuous one-parameter group of transformations, parameterized by time. At no point in this group of transformations is there a discontinuity where something new appears or something old disappears. The quantum state of the universe, if we take seriously the idea that quantum mechanics applies to everything, including the universe as a whole, is a single, continuous mathematical object that evolves smoothly through time according to the Schrödinger equation. At no point in this evolution does something new come into existence in the sense of appearing where there was previously nothing. The state changes, the probability amplitudes for different configurations change, the decoherent structure that gives rise to classical-looking world branches changes, but the state itself is always present, always evolving, always connected to its past and its future by the continuous action of the Schrödinger equation. There's a specific subtlety here that I want to address, which is the quantum measurement problem and the apparent collapse of the wave function. In the Copenhagen interpretation, when a quantum measurement is performed and an outcome is observed, the quantum state appears to collapse from a superposition to a definite state. The collapsed state is not continuously connected to the pre-measurement state by the Schrödinger equation. It involves a discontinuity, a jump. Does this represent the coming into existence of something new? I think the answer is no, for two reasons. First, in the many worlds interpretation, which I believe is the most consistent interpretation of quantum mechanics, there is no collapse. The apparent jump is an artifact of looking at only one branch of a continuously evolving universal wave function. The universal wave function itself evolves smoothly and continuously without any moment of creation or destruction. The observer who sees one outcome experiences only their branch, but the other branches are equally real and equally continuously evolving. Second, even in the Copenhagen interpretation, the collapsed state does not represent the creation of something from nothing. It represents the selection of a specific outcome from a pre-existing superposition. The superposition was already there. The outcome was already a component of the superposition with a definite amplitude. The collapse did not create the outcome. It actualized it, or revealed it, or selected it, depending on your interpretation. The measurement problem has been a source of philosophical controversy for nearly a century. Different interpretations of quantum mechanics give different accounts of what happens during measurement. But what all interpretations agree on is that the quantum state before measurement contains within it the outcome that will be realized. The outcome does not appear from nowhere. It was already in the quantum state as a component of the superposition with a calculable probability. The measurement does not create the outcome. It selects or reveals or actualizes a component that was already present. Neither creation from nothing nor destruction to nothing appears in quantum mechanics at the level of the quantum state. The state evolves. It does not begin or end. Now let me take you to the framework that I find most illuminating for this question, which is the space-time picture of special and general relativity and the block universe that follows from it. In special relativity, as I have described in detail in several earlier videos, space-time is a four-dimensional geometric structure. Every event at every time exists in this structure as a mathematical point with specific coordinates. The distinction between past, present, and future is not a feature of the space-time geometry. It is a feature of the local causal structure of which events are connected by time-like paths. But all events, past and future, are equally present as elements of the four-dimensional block. In this picture, the question of when something comes into existence does not have the form you expect. A star does not come into existence at a moment in time. A star is a region in the four-dimensional block where the conditions for nuclear fusion are present. The earlier temporal cross-sections of that region show the star as a forming molecular cloud. The later temporal cross-sections show it as a burning star and eventually a remnant. All of these cross-sections are equally present in the block. The star does not come into existence at the time of its formation, any more than a mountain comes into existence at the elevation, where it first rises above the surrounding terrain. The mountain is a feature of the three-dimensional landscape. The star is a feature of the four-dimensional space-time block. The coming into existence that we observe is the crossing of a threshold in a continuously existing configuration. The atoms that form the star were there before the star existed. The star is a specific pattern that those atoms take for a specific period of time. When the pattern begins, when the threshold is crossed and nuclear fusion ignites, we say the star has come into existence. But what has come into existence is not matter or energy or space-time. It is a configuration, a pattern, an arrangement of things that were already there. The pattern began. The things that formed the pattern did not begin. They were already in the block. This applies to every case of apparent beginning. The moment a new species appears in the fossil record is the moment when the evolutionary changes have accumulated enough that we classify the organisms differently from their ancestors. But the organisms themselves are continuous. Their chemistry, their atoms, their physics is continuous with what came before. What changed was the classification, not the existence. The moment a new thought emerges in a brain is the moment when a new pattern of neural activity crosses the threshold of whatever produces consciousness. But the neurons were already there. The synaptic connections were already there. What changed was the pattern, not the existence of the substrate. In the block universe, nothing comes into existence because everything is already in the block. The events that we call beginnings are the temporal boundaries of patterns, the lower temporal cross-sections of four-dimensional regions where a specific configuration is present. The configuration begins at its lower temporal boundary in the sense that temporal cross-sections below that boundary do not contain the configuration. But the space-time region that contains the configuration is a permanent part of the block, as real and as fixed as any other region. The beginning of the configuration is not the beginning of the space-time that contains it. Now let me take you to quantum field theory, which is the framework that underlies our deepest understanding of particles and forces, and which provides the most sophisticated version of the argument that nothing comes from nothing. In quantum field theory, the fundamental objects are not particles, but fields, mathematical objects that assign a value to every point in space-time. The electron field, the photon field, the Higgs field, all of these are fields that permeate all of space-time. Particles are not separate entities. They are excitations of these fields, disturbances that propagate through the field like ripples on the surface of a pond. When we say that a particle is created in a particle collision, what we mean in the language of quantum field theory is that the energy of the collision has been used to create an excitation in the relevant field. The field itself was already there, filling all of space-time. The excitation, the particle, is a new feature of the field. But the field that supports the excitation was pre-existing. The particle is not created from nothing. It is an excitation of something that was already there. This is a deep point about the nature of vacuum in quantum field theory. The quantum vacuum, which I described in detail in the video about empty space, is not empty. It is the lowest energy state of all the quantum fields, a state that is filled with quantum fluctuations, virtual particles, and vacuum energy. The vacuum is not nothing. It is a specific state of a physical system, a state that has properties, that responds to perturbations, that has energy density. Creating a particle from the vacuum does not create something from nothing. It rearranges the vacuum, transferring energy from the vacuum fluctuations into a real excitation. There is no state of physical reality that corresponds to nothing in the quantum field theory sense. The quantum fields are always there, always in some state, always carrying energy and quantum numbers. The closest thing to nothing that quantum field theory allows is the vacuum state, and the vacuum is not nothing. It is a specific, rich, physically complex state of the quantum fields. Now let me apply all of this to the deepest and most difficult question, the one that all of these frameworks ultimately point toward. What does physics say about the origin of the universe? About the moment, if there was a moment, when the universe itself came into existence? Now let me apply all of this to the deepest and most difficult question, the one that all of these frameworks ultimately point toward. What does physics say about the origin of the universe? About the moment, if there was a moment, when the universe itself came into existence? Before I address the physics directly, I want to acknowledge the philosophical tradition that has asked this question most carefully, because the dialogue between physics and philosophy on this topic is important, and because I think the physics changes the terms of the philosophical debate in ways that are not yet fully appreciated. The cosmological argument for the existence of God, in its most influential forms, is an argument from the existence of the universe to the existence of a first cause. The argument typically runs: everything that begins to exist has a cause. The universe began to exist, therefore the universe has a cause. The cause of the universe, being outside space-time and without itself being caused, is identified with God or something like God. The first premise, everything that begins to exist has a cause, seems compelling based on everyday experience. We never observe things coming into existence without a cause. The second premise, the universe began to exist, seems to be supported by the Big Bang cosmology, which describes a universe with a first moment of time. The physics I have been describing challenges both premises, but in different ways and with different levels of force. The challenge to the second premise is the more straightforward one. The Hartle-Hawking no-boundary proposal, and more broadly the idea that time is a derived quantity that breaks down near the Big Bang, suggests that the universe did not begin to exist in the sense required by the cosmological argument. The universe has a first moment of time, in the sense that there are no events at earlier temporal coordinates. But having a first moment of time is not the same as beginning to exist in the philosophically relevant sense. A sphere has a south pole, the southernmost point on its surface, but the sphere did not begin to exist at the south pole. The south pole is a geometric feature of the sphere, not a moment of creation. Similarly, the Big Bang is a geometric feature of the space-time block, the earliest temporal coordinate of the four-dimensional structure. The universe did not begin to exist at the Big Bang any more than the sphere began to exist at its south pole. The Big Bang is the first moment in the universe, not the moment the universe came into existence. The challenge to the first premise is more subtle. The physics of quantum field theory and quantum cosmology suggests that the concept of beginning to exist does not have a well-defined referent in the physical world, at least not at the fundamental level. When we say something begins to exist, we mean that there is a temporal boundary of some configuration, a moment before which the configuration is absent and after which it is present. But as I have been arguing, the configurations that are present or absent are patterns formed from pre-existing stuff. The stuff itself does not begin to exist. It transforms. The patterns begin. The stuff does not. If beginning to exist means the appearance of new matter, energy, or space-time from a state that contained none of these, then nothing begins to exist in the physical world. Conservation laws prevent the creation of matter and energy from nothing. The block universe contains all space-time as a permanent structure. Quantum field theory describes particles as excitations of pre-existing fields. If beginning to exist means something weaker, the appearance of new patterns formed from pre-existing stuff, then things begin to exist all the time. But causes in this sense are not the transcendent cause that the cosmological argument requires. The cause of a new pattern is the prior configuration that gave rise to it through the laws of physics. This kind of causation is thoroughly physical, thoroughly immanent, thoroughly within the space-time block. It does not point beyond the block to anything external. This does not refute the cosmological argument. An advocate of the argument can respond that the first premise, correctly understood, applies to the beginning of the universe in the physically meaningful sense, whatever that turns out to be. And they can argue that the question of why the laws of physics and the initial conditions of the universe are what they are, a question that physics does not and perhaps cannot answer, points beyond physics to a ground of being that is outside the physical framework. I think this response is legitimate. The physics does not settle the cosmological argument. What it does is show that the physics does not support a specific version of the argument, the version that takes the Big Bang as evidence for a temporal beginning of the universe in the sense required for the causal premise to apply. The physics suggests a more nuanced picture in which the concept of beginning to exist as applied to the universe as a whole is either false or undefined. The standard Big Bang picture, as I described in detail in the video about something rather than nothing, says that the universe began approximately 13.8 billion years ago in an extraordinarily hot, dense state. The universe has been expanding and cooling ever since. But the standard Big Bang picture does not describe what happened before or at the moment of the Big Bang. General relativity, the theory that underlies the Big Bang cosmology, predicts a singularity at t equals 0, a point at which the density and temperature become infinite and the theory breaks down. The singularity is not a physical event that general relativity describes. It is the boundary of the region where general relativity applies. What happened at or before the singularity cannot be described within general relativity. This is where quantum cosmology comes in. The attempt to apply quantum mechanics to the universe as a whole, including its beginning. The most influential approach to quantum cosmology is the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in 1983. The Hartle-Hawking proposal uses a mathematical technique called a path integral, which is the fundamental computational method of quantum mechanics. In ordinary quantum mechanics, the probability amplitude for a particle to go from one point to another is computed by summing over all possible paths between the 2 points, with each path weighted by a phase factor that depends on the action, the integral of the Lagrangian, along the path. This sum over paths encodes all the quantum mechanical possibilities. Hartle and Hawking applied this path integral approach to the geometry of spacetime itself. They proposed that the wave function of the universe should be computed by summing over all possible spacetime geometries that have a specific boundary, a three-dimensional surface corresponding to the current state of the universe. Unlike ordinary path integrals, which sum over paths from an initial state to a final state, the Hartle-Hawking proposal sums over geometries that have only one boundary, the final state. There is no initial state, no initial boundary, no t equals 0. The path integral is over compact geometries, geometries that are closed rather than having a beginning. The technical implementation of this idea requires a mathematical trick called a Wick rotation, in which the time coordinate is analytically continued to imaginary values. In the imaginary time picture, time behaves like a spatial dimension. The four-dimensional space-time becomes a four-dimensional space with Euclidean geometry, like the surface of a four-dimensional sphere. This Euclidean geometry is compact, without boundaries. There is no beginning and no end. The universe simply exists as a mathematical object, a closed four-dimensional space without any moment of creation. The Hartle-Hawking proposal gives a specific prediction for the wave function of the universe, and from that wave function, specific predictions for the probability of different initial conditions for the universe. The proposal has been studied extensively and has been criticized and defended by different researchers. One of its most significant predictions is that the universe emerged from a state of minimal size and maximum symmetry, which is qualitatively consistent with the observed large-scale homogeneity and isotropy of the universe. The Hartle-Hawking proposal uses a mathematical technique called a path integral, which is the fundamental computational method of quantum mechanics. In ordinary quantum mechanics, the probability amplitude for a particle to go from one point to another is computed by summing over all possible paths between the 2 points, with each path weighted by a phase factor that depends on the action, the integral of the Lagrangian, along the path. This sum over paths encodes all the quantum mechanical possibilities. Feynman developed the path integral formulation of quantum mechanics in the 1940s as an alternative to the Schrödinger equation. In the path integral picture, the probability amplitude for any quantum process is a sum over all possible histories, each history weighted by a phase that depends on the action of that history. The interference between different histories, between different paths in configuration space, is what produces the characteristic quantum effects of diffraction and entanglement. The path integral is the mathematical expression of the quantum principle that every possibility contributes to the observed outcome. Hartle and Hawking applied this path integral approach to the geometry of space-time itself. They proposed that the wave function of the universe should be computed by summing over all possible space-time geometries that have a specific boundary, a three-dimensional surface corresponding to the current state of the universe. Unlike ordinary path integrals, which sum over paths from an initial state to a final state, the Hartle-Hawking proposal sums over geometries that have only one boundary, the final state. There is no initial state, no initial boundary, no t equals 0. The path integral is over compact geometries, geometries that are closed rather than having a beginning. The technical implementation of this idea requires a mathematical trick called a Wick rotation, in which the time coordinate is analytically continued to imaginary values. In the imaginary time picture, time behaves like a spatial dimension. The four-dimensional space-time becomes a four-dimensional space with Euclidean geometry, like the surface of a four-dimensional sphere. This Euclidean geometry is compact without boundaries. There is no beginning and no end. The universe simply exists as a mathematical object, a closed four-dimensional space without any moment of creation. When the Wick rotation is performed in reverse, translating the Euclidean geometry back to the Lorentzian space-time that describes our experience, the result is a space-time that near its beginning smoothly transitions from a Euclidean space-like region to a Lorentzian time-like region. Near what we would call the Big Bang, time becomes indistinguishable from a spatial direction. The Big Bang is not a point where the geometry breaks down, as it is in classical general relativity. It is a smooth geometric feature analogous to the pole of a sphere. The Hartle-Hawking proposal gives a specific prediction for the wave function of the universe, and from that wave function, specific predictions for the probability of different initial conditions for the universe. The proposal predicts that the universe most likely began in a state of maximum symmetry and minimum size, which is qualitatively consistent with the observed large-scale homogeneity and isotropy. It predicts specific statistical properties of the initial perturbations that seeded the structure of the universe, and these predictions are in rough qualitative agreement with observations of the cosmic microwave background. The proposal has been criticized and defended extensively. Some physicists, including James Hartle himself, have raised questions about whether the Euclidean path integral is well defined for gravity and whether the Wick rotation is mathematically justified. Others have argued that the Hartle-Hawking proposal gives the wrong predictions for the probability of specific cosmological scenarios, predicting that the current universe is highly improbable compared to alternatives. The debate continues, and the Hartle-Hawking proposal is not universally accepted as the correct approach to quantum cosmology. But I want to focus on what the Hartle-Hawking proposal says about the concept of beginning, regardless of whether it is the correct cosmological model. The proposal says that the universe has no beginning in the physical sense, not that the beginning is hidden or beyond measurement, not that we do not know what happened at the beginning, but that the concept of beginning does not apply to the universe as a whole, because time is a derived quantity that emerges from the geometry of a compact four-dimensional space and does not have a well-defined earliest moment. Hawking described this in his book, A Brief History of Time, with the analogy of asking what is south of the South Pole. The question seems grammatically correct, but is physically meaningless. There is no south of the South Pole because the South Pole is the most southerly point on the globe. Similarly, there is no before the Big Bang in the Hartle-Hawking picture because the Big Bang corresponds to the point in the compact geometry where the temporal coordinate reaches its minimum. Asking what happened before is like asking what is south of the South Pole. I find this response both beautiful and unsatisfying. Beautiful because it dissolves the question rather than answering it, showing that the question itself is based on a false premise. Unsatisfying because it does not explain why the universe has the specific geometry that it has, why the path integral gives the specific wave function that it gives, why there is a compact four-dimensional geometry rather than nothing. The question of why there is something rather than nothing has been transformed into the question of why the path integral gives a non-zero result for any geometry, which is still a deep and unresolved question. There is another approach to quantum cosmology worth mentioning here, developed by Alexander Vilenkin, which is sometimes called tunneling from nothing. In Vilenkin's proposal, the universe originated as a quantum tunneling event, a transition from a state of nothing, by which he means a state without space or time, to a state with a small closed space-time. This is analogous to quantum tunneling in ordinary quantum mechanics, where a particle can tunnel through a potential barrier even when it does not have enough energy to pass over the barrier classically. Vilenkin's proposal is mathematically different from Hartle-Hawking, and in some cases gives different predictions for the wave function of the universe. It also has a different conceptual character, whereas Hartle-Hawking dissolves the question of what happened before the universe by showing that the concept of before breaks down near the Big Bang. Vilenkin's proposal retains the concept of a transition from nothing to something, though the nothing in his proposal is a specific technical state, the absence of space-time, rather than the philosophically loaded concept of absolute nothingness. Both proposals are serious attempts to address the question of the origin of the universe using the tools of quantum mechanics and general relativity. Both face significant technical and conceptual challenges, and both share the feature that the universe, in their descriptions, has no cause in the ordinary sense of a prior event that brought it into existence. The Hartle-Hawking universe has no before. The Vilenkin universe has no prior cause, only a quantum probability for tunneling from a state without space-time to a state with space-time. What I find most profound about the Hartle-Hawking proposal, for the purposes of this discussion, is its treatment of the moment of beginning. The question, what happened before the universe began, has no answer, not because the answer is unknown, but because the question is malformed. Time, in the Hartle-Hawking picture, is a derived quantity that emerges from the geometry of the compact four-dimensional space. Near the South Pole of the metaphorical four-sphere, where we would expect the beginning to be, time becomes indistinguishable from space. The concept of before breaks down. There is no before. There is no moment when the universe began. The universe simply exists as a geometric object, and the temporal structure we experience is an approximation that becomes valid away from the beginning. Hawking described this in his book, A Brief History of Time, with the analogy of asking what is south of the South Pole. The question seems grammatically correct but is physically meaningless. There is no south of the South Pole because the South Pole is the most southerly point on the globe. Similarly, there is no before the Big Bang in the Hartle-Hawking picture because the Big Bang corresponds to the point in the compact geometry where the temporal coordinate reaches its minimum. Asking what happened before is like asking what is south of the South Pole. I find this response both beautiful and unsatisfying. Beautiful because it dissolves the question rather than answering it, showing that the question itself is based on a false premise. Unsatisfying because it does not explain why the universe has the specific geometry that it has, why the path integral gives the specific wave function that it gives, why there is a compact four-dimensional geometry rather than nothing. The question of why there is something rather than nothing has been transformed into the question of why the path integral gives a non-zero result for any geometry, which is still a deep and unresolved question. Let me now connect all of these frameworks together into the coherent picture I promised at the beginning, because I think the combination of classical mechanics, quantum mechanics, the block universe, quantum field theory, and quantum cosmology points toward a conclusion that is both specific and radical. Now let me connect all of these frameworks together into the coherent picture I promised at the beginning, because I think the combination of classical mechanics, quantum mechanics, the block universe, quantum field theory, and quantum cosmology points toward a conclusion that is both specific and radical. Before stating the conclusion, I want to add one more element to the picture, which is the string theory landscape and the multiverse. I described the string theory landscape briefly in the video about something rather than nothing, but I want to revisit it here because it adds an important dimension to the question of beginning and existence. String theory, the leading candidate for a theory of quantum gravity, predicts the existence of an enormous landscape of possible universes, each with different physical laws, different particle content, different values of the physical constants. The number of possible universes in the landscape is estimated to be on the order of 10 to the 500, an incomprehensibly large number. In eternal inflation, the inflationary expansion of the early universe never completely ends, but continues producing new regions of spacetime that each settle into one of the landscape, vacua, creating a multiverse of bubble universes, each with different physical laws. In this picture, our observable universe is one bubble in an eternally inflating multiverse. Our bubble began when a region of the eternally inflating background settled into our vacuum, the specific string theory vacuum that has the physical laws we observe. From our perspective within the bubble, there was a beginning, the moment when our vacuum was selected. But from the perspective of the eternally inflating multiverse, there was no beginning. The inflation was eternal in the past, producing bubble universes continuously, with no first moment. The eternally inflating multiverse challenges the concept of beginning even more directly than the Hartle-Hawking proposal. If inflation is eternal to the past, then the universe, in the broad sense that includes all the bubble universes and the inflating background, has always existed. There was no first moment. There was no beginning of the physical universe in the global sense. This does not eliminate the question of why the eternally inflating multiverse exists, why it has the specific properties it has, why the string theory landscape is what it is. These questions remain, and they are even harder to answer than the corresponding questions about a single universe. The multiverse pushes the question of existence one level up. Instead of asking why there is a universe, we ask why there is a multiverse. And the physics does not answer that question either. The conclusion is this: the concept of coming into existence, of something going from not existing to existing at a specific moment, is not a primitive concept in any framework of physics. In classical mechanics, configurations evolve, but matter is conserved. In quantum mechanics, the quantum state evolves continuously, but never begins or ends. In the block universe, all events exist timelessly at their space-time coordinates. In quantum field theory, particles are excitations of pre-existing fields, not creations from nothing. In quantum cosmology, the universe has no beginning in the physical sense, because time itself is a derived quantity that breaks down near the boundary of the geometry. What does exist in all these frameworks is change, evolution, process. The configurations of matter and energy change. The quantum state evolves. The temporal cross-sections of the block vary. The excitations of the fields propagate and interact. But none of this change involves something appearing where there was previously nothing. Every change is a transformation of what was already there. This has a specific and important implication for how we should think about the origin of the universe. The question, what was there before the universe existed, is based on the assumption that there was a time when the universe did not exist and a time when it did, with a transition between them. The physics says this assumption is wrong. The universe is not something that came into existence at a moment. The universe is the totality of what exists, the entire space-time block, including all its contents. The question of what was there before the universe is like the question of what is outside of everything. The question is grammatically well formed, but physically empty. This does not mean the universe is eternal in the simple sense of having existed for an infinite time. The Big Bang was a real event. The universe had a first moment of time, in the sense that there are no events in the space-time block with temporal coordinates earlier than the Big Bang. But the existence of a first moment of time does not imply that the universe began to exist. It implies that time has a finite extent in the past direction, just as space has a finite extent in certain compact geometries. The edge of time is not a moment of creation. It is the boundary of the region where time is defined. Now I want to take this argument to its most radical implication, the one that I think has not been fully stated in the popular or philosophical literature, and that I think is the most important and the most disturbing. If the universe did not come into existence, if there was no moment when the universe went from not existing to existing, then the question of why the universe exists cannot be answered by pointing to a cause. Causes are events. An event causes another event, and the cause precedes the effect in time. But if the universe is the totality of space-time, if there is nothing outside the space-time block, then there is nothing that could serve as the cause of the universe's existence. The universe has no cause, not because the cause is unknown, but because the concept of having a cause requires there to be something outside the system in question that can act on it. For the universe as a whole, there is nothing outside. This is the most radical version of the argument from physics. Not just that we cannot observe the beginning of the universe or cannot describe it using current physics, but that the concept of the universe beginning to exist, and therefore the concept of the universe having a cause, is not supported by the physical framework. The physics describes a universe without a beginning and without a cause, not because the beginning and cause are hidden or beyond measurement, but because they are not the kind of thing the physics describes. I want to be careful here, because this argument can be misread in two different ways that I want to avoid. The first misreading is that this settles the question of why the universe exists. It does not. The physics tells us that the universe, as described by our best physical theories, has no beginning and no cause within the physical framework. But the physics does not tell us why the universe has the specific mathematical structure that it has, why the laws of physics are what they are, why the path integral gives a non-zero result, why there is anything at all. These are genuine questions, and the physics does not answer them. It simply changes their form. The question, why does the universe exist, cannot be answered by pointing to a prior cause. It must be answered, if it can be answered at all, in some other way. The second misreading is that this is an argument against the existence of God or any transcendent cause. It is not. The argument is that within the physical framework, the universe has no beginning and no cause. This does not address the question of whether there is a reality beyond the physical framework that is responsible for the physical framework existing. That question is genuinely beyond the reach of physics. I am not claiming that there is no such reality. I am claiming that physics does not describe it, and that the specific concept of the universe coming into existence at a moment, which is what most versions of the cosmological argument for God's existence depend on, is not supported by the physics. What the physics does support is a picture of the universe as a self-contained mathematical structure, a block of space-time with specific geometric and quantum properties, evolving according to specific laws, without any need for an external first cause in the physical sense. Whether this mathematical structure requires an explanation beyond itself, whether the specific laws it embodies require a ground outside the physics, is a question that physics cannot answer. It is a question that may be beyond the reach of any empirical method. This is the most honest thing I can say about the deepest question in cosmology. Not an answer, a clarification of the form of the question after the physics has had its say. The most radical implication of the physics is not that existence is meaningless. It is that existence needs no external beginning, no prior cause, no creative act from outside to be real. The universe exists. The patterns within it emerge and dissolve. And you are one of those patterns, as permanent and as real as anything in the universe for the duration of your world line in the block. Now, let me close with something that I think is the most important practical implication of everything I have described. The implication is about the relationship between physics and meaning. The fact that physics does not describe the moment when something comes into existence does not mean that nothing matters. The patterns that emerge in the space-time block, the configurations of matter and energy that produce stars and planets and life and consciousness, are real features of the block. They have genuine structure. They interact with each other in ways that have consequences. The people you love are real patterns in the block, as real and as permanent as anything in the universe. The choices you make are real events in the block, connected to other events by the laws of physics with genuine consequences. Let me add one more layer to this picture, which I think is important for understanding the full scope of what physics says about existence. The hard problem of consciousness, which I have discussed in several earlier videos, is the problem of explaining why physical processes give rise to subjective experience, why there is something it is like to be a brain processing information rather than just processing happening in the dark. The hard problem is relevant to the question of beginning to exist in a specific way. When you became conscious for the first time, in whatever sense consciousness begins in a developing brain, there was a moment when there was first something it was like to be you. The physics of neurons firing and synapses connecting cannot, as far as we currently understand, explain why there is something it is like to be the physical system that results. The subjective experience, the first-person perspective, seems to require something beyond the third-person physical description. If consciousness has properties that the physical description cannot capture, then the beginning of consciousness, the moment when there first was something it was like to be a specific person, might be a genuine case of something coming into existence in a way that the physics does not describe, not from nothing in the metaphysically absolute sense, but from physical processes that do not themselves contain what emerges from them. I raise this not to resolve it, but to acknowledge it, because I think intellectual honesty requires acknowledging the limit of what the physics says. The physics says that physical patterns do not begin to exist in the sense of arising from nothing. It does not say that everything that exists is fully described by the physics. If consciousness has properties that escape the physical description, those properties might begin to exist in a way that the physics does not capture. The question of consciousness and beginning is one of the deepest and least resolved in all of philosophy and science. I do not know the answer. I do not think anyone does. But the physics of beginning, which I have been developing throughout this video, changes the form of the question. It shows that within the physical framework, nothing begins in the absolute sense. What remains uncertain is whether the physical framework is complete, whether everything that exists is captured by the physics, or whether there are aspects of existence that the physics leaves out. The fact that physics does not describe the moment when something comes into existence does not mean that nothing matters. They have genuine structure. They interact with each other in ways that have consequences. The people you love are real patterns in the block, as real and as permanent as anything in the universe. The choices you make are real events in the block connected to other events by the laws of physics with genuine consequences. The fact that these patterns did not come into existence from nothing, that they are transformations of pre-existing configurations of matter and energy, does not diminish them. A symphony is not less beautiful because the sound waves that carry it were already vibrating in the molecules of the air before the first note was played. A thought is not less profound because the neurons that generate it were already there, already connected, already primed to fire in specific patterns by the history of the brain they belong to. The emergence of a pattern is real, even if the stuff that forms the pattern was already there. What physics takes away with one hand, the concept of creation from nothing, it returns with the other, the concept of emergence, of complexity, of the appearance of genuinely new patterns in a universe that is transforming its configurations through time. The universe does not create new things from nothing, but it continuously reorganizes what it has into new patterns of extraordinary complexity and beauty, including the pattern that is you, reading these words, understanding the physics of your own existence. The most radical implication of the physics is not that existence is meaningless. It is that existence needs no external beginning, no prior cause, no creative act from outside to be real. The universe exists. It has always existed in the sense that the space-time block has no outside. The patterns within it emerge and dissolve, but the block remains. And you are one of those patterns, as permanent and as real as anything in the universe, for the duration of your world line in the block. That is not nothing. That is everything. If this changed how you think about beginnings, about existence, about the relationship between the physics of creation and the ordinary intuition that things come into existence, tell me in the comments. Tell me whether the Hartle-Hawking no-boundary proposal changes how you think about the origin of the universe, and whether the absence of a first cause in the physical framework disturbs you or liberates you. Tell me whether you find the picture of the universe as a self-contained mathematical structure satisfying, or whether you think it deepens rather than resolves the mystery of why there is something rather than nothing. These are the questions at the intersection of physics and philosophy, and the deepest human concern with meaning and existence. And subscribe if you want to keep going into the places where the physics meets the questions that matter most. Because this series has only just begun to go as deep as it can